Cool. So I see that at least for Saul, seems like you have already some experience with smart contracts and doing reentrancy attacks. So it is okay if you have any comment regarding to the implementation of the things that we are going to do here. But this is an oversimplification of what it is really reentrancy attack, and even that uh, the, the the language, the Solidity language has been improved in order to avoid this kind of attacks. There are still some problems out there that we can that we should fix. But yeah, this is an oversimplification. So well, I think we can get started. Okay, so we can start by some security fundamentals. This is important because just before going into the reentrancy attack, we have to talk about security, because as developers, we are always like in risk of creating a really bad bug or something that somebody can take advantage of. So it is great that we talk about this. And to start, let's see Ethereum like their main features as insecurity features, kind of. And this is because if you think about it, it is great to have immutability about the data in the blockchain, but also it can be insecure, because what if we upload a new bug or a new security flow into our smart contract? Well, there is no way we can get that down. So it is usually seen like an advantage, but if we think about it closely, it is not really an advantage if there is some problems regarding the implementation. So uh, also from the immutability, there is a problem with the persistency. I mean, if we enter data that it is not supposed to be there forever, there is a problem, because it will be persistency and also transparent for every people that want to audit the contract or also check whatever it is there. And also about the privacy, I mean, you can perform a reentrancy attack, and as long as you manage to get everything private, I mean, you can really create a lot of damage without people not knowing who are you. So this is also a great feature for blockchains, but not really a great feature for security. And also it is Turing completeness. So the Turing complete is, as you know, is the is this property of the machines or in computer science that refers to every single machine that can, given enough resources and time, it can compute any problem, any computable problem. So since any programming language is in this category, and every programming language can have security flaws, also a smart contract have, because it is Turing complete, and from the perspective of security, it can always be hacked. So this is something to take into consideration. And why is security important? Well, because as developers, you should be always prepared for any potential failure. So it is great to have always in mind that probably something can go wrong and you are not able to find out before it happens. So it is great to have protocols at your company and also protocols at your team. So if given the case that there is a problem within your contract, you can fix it, or at least have a strategy to, I don't know, to try to fix it. But yeah, probably you won't be fixing it. And also, you have to think about security first when you are designing your products. So even though it is hard, because we don't know already all the possible vulnerabilities of a smart contract, it will be great if you start by thinking about security when you are creating the product in the first place. Also, always be simple with your implementation, because simple code is code that can be readable, and this is code that can be easily debug when you have some problems. So if you try to do some complicated things, by definition, something complicated is not easy to debug. So please try to be simple. And also regarding to updates, there are some ways to update your contracts, your smart contracts. But in this case, usually we assume that there is no way to update our smart contracts. And also be cautious with the blockchain properties, which are the same that we discussed previously. And this is because, yeah, even though they are advantages that can become problems in the future. And finally, think about reusage versus duplication of the code, because we as developers are pretty used to create our own security implementations for almost everything, because I don't know, that there is this belief that if you don't code it, you cannot trust it. But usually when you reuse code, there are many people that have been where you are at right now. So probably there is a great way, or it is a great way to have the knowledge of all of these people here. So always try to reuse. And this is great, for example, if you use Open Zeppelin when you are developing contracts, because it is code that is this audited but by many people and by all the community. So now about the reentrancy, and just start to talking about the reentrancy and the security flaw that we are going to cover today. This is one of the most famous. And why? Because it is pretty simple, but it is not clear when you see it the first time. This is because a reentrancy problem or a reentrancy security flaw, it is just a function. It can be obviously a bigger function with many other things implicated, but this is the most simple way that it can be represented. And this is because here in the line, let's say 1, 2, 3, 3, and 4, this here is the security flaw, and this is the equivalent that if you go to a bank where you have an account, let's say that you want to withdraw your funds from the bank. Okay, so you go with the guy at the reception, then you request your money back, and then the guy just give you the money, but he didn't ask you for your name, so you can take the money and just run away, and he will not know who are you, and then he will not have the opportunity to register that he gave you that money. So in this real world scenario, the problem is that the company or the bank has already given you the money, and they don't know you who you are. And this is the problem here, because you are sending the value first, and then you are registering the withdrawal later. And this is the problem here, is that we can use this order of the calls just to create a recursive call that is going to hack and install everything in the contract. So we are going to implement it later, but we first have to talk about one of the famous, or well, the most famous case of an attack using a reentrancy attack. And this was the DAO hack. Actually, this is pretty famous, and this was the cause that why Ethereum was split into two, which is Ethereum Classic and the Ethereum that we already have. And this at the moment was a stole of about 3.6 million ETH, which was about $75 million at the moment. So this is the size of the problem. And think about that, you as a developer, you might be creating bugs like this. So this is why it is important to always think in security first. And yeah, well, if you want to know about more other attacks, you can go to the consensus known attacks page. They have documented every single kind of attack, and including the reentrancy, and also they have many others here. Also, here you have some security tools that you can use, but we are not going to enter into here, but there are many out there that you can use. Also, if you're using, for example, VS Code, you can use it, and you can set up some plugins that are there. And okay, so now let's see how to do a reentrancy. We're going to provide some information about how to do it and how it works really. And at the end, I'm going to try a simple demo for you, and I'm going to give you a repository with an example, so you can try it out and you can follow this tutorial whenever you want. Okay, so let's start with a victim contract. A victim contract will be our the contract that we are going to hack. And this is, as I said, this is an oversimplification. This is just an ether vault when we are going to save some ether. Maybe too simple, but it is actually the way many of the DeFi apps work. because many of them, they just hold your Ether for you and they give you some kind of tokens or some representation of that, and in any form. So usually this is the way. So this simple contract will functions. The function will be a withdraw function, which is just a way to claim back your Ether. And also it has a function which is an anonymous function. This is a fallback function. So whenever you call the Ether vault with no data, the fallback function will be executed, and this will receive any Ether that you send, and it will save it into a balance. So you can always know here what is your actual balance if you want to know it. Also note that here at this line, we are requiring you that you are not trying to withdraw more than what you have on your balance. So yeah, this is the basic authentication authorization requirement here. But yeah, I mean, it is normal and we can overpass it using a reentrancy attack. So let's analyze this contract. At the very beginning, we have the version of Solidity, which is going to be the 5.0. This is because this is the well, I haven't tried with a more recent version. So this is the one that I'm pretty sure that it works. But we can go up to, I think, up to the version 6 or something. So yeah, I mean, it will be great if we try with another version later. But for this time, we're going to use the 5.0. And okay, again, sorry, also, we are going to use this require as a validation just to be sure that nobody is taking more Ether than they have in their accounts. And finally, we are going to use this function to send the value. Probably you may know, if you have played with Solidity, you may know about the transfer function. And the problem with the transfer function, well, it is not really a problem, but the problem here is that it doesn't allow you to do some things like the ones that we are going to do today. So it is more secure to use the transfer function whenever you want or whenever you can. But for this time, and in order to get the hack done, we are going to use this way of transfer. And if you don't understand how this way of transfer works, I'm going to explain you. So first we have a message.sender, which is the address of the guy who is behind the not the hack, behind the deposit. So for example, if I just transact with the smart contract, this message that sender will have my address, and it is an address payable. And remember that the payable gives another functionalities to the address, so we can call another methods in the address. So now we have this call, this dot call, and because this is an address, you can call it through the call function. And think about this like a call to a smart contract. Whenever you have a smart contract and you just want to fetch data from it, but you don't want to transact with them, you can just call it. And this is the same because you have an address here, then you can call that address like like if you were doing a transaction. So with this call property, we will receive back a function, which will be the call. So we can later just call the function and it will just call the address. And finally, this that value is a way we have to mutate the function, the call, so we can set the amount of value we are going to send within the call. So in this case, we're going to use this withdraw to withdraw in order to send it back to the holder the amount that he is requesting. So at the end, this is a function, and we are just calling that function, and this is going to be sending the total amount of Ether. And okay, great. So now that we have covered this line and this function, we have to implement a fallback function. And as I said, a fallback function is a function that is always called whenever you call the contract, but there is no data in the transaction. Or it is called whenever you call the contract and you pass a function identifier that is not in the contract. Let's say, for example, I try to call a function foo in the Ether vault, and since there is no full function here, it is going to be handled by the fallback function. So this is a pretty simple way to just receive Ether, and we are going to override this fallback function in order to save the amount of Ether that we are sending. So this is just only saving into our balance the amount of Ether that we are sending. And this is not including fees. We are going to pay fees like for in the transaction, and this will only have the total amount that we are going to save. Okay, great. And as I said, the vulnerability is here. You're first sending the amount, and finally you are registering that withdraw, which can be used by a hacker as a way to call this function recursively. So in this way, you can, for example, use this to call another contract, and then that contract can call withdraw again, and that will be the recursion, and the smart contract will never reach this line until the end, or until we have not enough gas to continue. Great. So let's see about the hacker contract. This is the hacker contract. It's pretty simple, and it's an oversimplification, as I said. This will have the same version of Solidity. Also, we need the victim source code, and this could be one of the bigger challenges when doing this, but this is not usually a problem because you can just go to Etherscan and you can find the bytecode of the contract and you can decompile it. And not taking into account that many of these companies are verifying their contracts and publishing the source code there, so it shouldn't be pretty difficult. Okay, great. Second part, inside our constructor in the contract, we will create an instance of the victim. And for creating this instance, we will need an address, which will be an address payable. And this is the address of the previous contract. So once you detect a potential security flaw in one contract, you just copy the address, you just copy the source code, and you can create this hacker contract. And we will save this victim into a victim of type Ethervault, which is the previous contract that we were using. Great. And next, we're going to create a fund function, and this is only with the purpose of receiving money or receiving Ether here. This is because we are going to use our fallback function for another purpose. So it is great to have this function only to get the hacker to receive our money, and you're going to see why. But we need some Ether in order to create the attack to the original contract. So that's why we have this fund function here. And here with the deposit, I'm sorry, this is in Spanish. I didn't translate it. Okay, but yeah, with this deposit function, we will be just sending the Ether that previously we send it to the hacker contract. We're going to send it to the Ether vault. In this way, we are going to create a balance for the hacker contract in the Ether vault, and this will allow in the future to overpass the validation that the Ether vault has, that you cannot withdraw money that you don't have in the contract. So this way, we're assuring that the hacker has some value inside the balance of the Ether vault. And finally, we have our fallback function, and this is the key of all. We're using this fallback function to receive the money that the Ether vault is going to send us. So once that the Ether vault is sending us the Ether, the fallback function will be called, and this function will be calling the attack function again. This will try to withdraw. It will call withdraw again. Withdraw will send again the Ether to the hacker contract, and this will again call to the fallback function. So this way, we are just creating a recursive call, and this will last until we don't have any gas left. Okay, and finally, we have our attack function here. This is a public function just for simplicity. And it will call the victim and it will try to withdraw a certain amount of ether. And right, so this is the way it works, like in a nutshell. You start by calling the attack function. This will try to withdraw one ether, and this will call the withdraw function on the ether vault. This will surpass the require because you already have enough ether to withdraw. And then the withdraw will try to send you the amount that you try to withdraw. Since you have a fallback function here, you will receive this. You will count. This counter is just to count how many times we created that cycle, and we are going to use it later. And this function will receive the money and also will call attack again. And attack will repeat the cycle, and this is the way it works. Okay. Um, at the end, you can just withdraw everything using the withdraw function in your hacker contract, because at the end, the hacker contract will have every single unit of ether that you stole from the original contract. So with the withdraw function, you will receive whatever is there. Okay, so let's go to the example. And if you want to follow me on the tutorial, you can go to my GitHub and copy this base, this template, which is a reentrancy attack template. It is almost everything done. Is Truffle is set up. There is a basic setup of Webpack with JavaScript, so we can create a basic web interface to interact with the contract. But we're going to do it, and so don't worry if you want to replay this later. Okay, so I'm going to click this. This is the repo. So I'm just going to open a terminal here. Here it is. Let me just zoom this. And I think that is okay. Okay, great. So I'm just going to copy this with a git clone. Here it is. I'm going to get into the folder. I'm going to open Visual Studio Code, which is my favorite code editor. And let's have these next to each other. Okay. Great. Cool. So I see a question. What was the purpose of the font function again, Tyler? The purpose of the font function, let me just get here again, is because since the hacker function has the fallback used to attack again, we need a way to send ether to the hacker contract. And we are using this font function just to send, let's say, 2 ether in order to get the hacker have a balance into the other contract and then perform the operation. Great. Juan Yepes is requesting the link. Let me just send it to you. Yeah, Tyler, you cannot send it normally. Correct. Okay, great. Cool. So now that I have this here, I will close this terminal because I'm going to use this one. I think it's better. So you can see both of them. Okay, great. Let me just do some zoom. And that's great. Okay, so you can see that this is a pretty standard project using Truffle. It has its contract folder, this folder, the migrations folder, a test, which we are not going to use this time, and also a source. It is pretty simple, and let me just explore it so you can know what we're doing. First, we have the simple migrations contract that Truffle has built in. So we are not going to move anything here. Since we're using the version 5, we are between these boundaries, so it's okay, no problem. And also here in the dist folder, there is an index HTML with a simple, very simple user interface. It has no styles, nothing regarding to CSS or whatever. It is pretty simple, and this is just because this is not a session about web development. It is just about creating a contract. So don't matter if you want to add some styles and add some CSS here. Okay, and finally we have the migrations contract here, which is also built into Truffle. And the interesting part is here, the source. Okay, so this is code that is going to be run into the browser once we create a server. In a few minutes, I'm going to explain how to create that server. And once the server is created, we're going to serve a static page, which is this one. And this one is going to compile this code. This code is just going to connect to MetaMask using Ether.js, or we are going to use the library of Ether.js. Then it is going to collect the elements of the UI. These are just HTML elements. These are buttons, inputs, forms, nothing really weird. But we are going to use these. For example, deposit amount is the amount of money that you want to deposit to the Ether vault. So you're going to see in a few minutes. Hacker, again, are just UI elements. And these are the functions that we are going to fill later. And these are the functions that we are going to use to interact with the contract. Here are some listeners for the buttons and the inputs that we were using. And these are immediately executed functions just to get the actual value of Ether that we have in the contract, so we can check it out frequently. Okay, great. It is pretty simple, as I said. Let's say what is in the package JSON. There are two main scripts. The first script is a start script, and it will just create a development server so we can test this out. If you want to build this out and upload it to any cloud service, you can do it with the build script, but we are not going to use this. And also, the only dependency we have is ethers, which is the one that we're going to use to interact with the contracts. Okay. And finally, the Truffle config, which is also the basic Truffle config that we always have whenever we start a project with Truffle. Okay, there are some other files here, like the webpack config. I think we shouldn't be focused there. That is pretty simple. It is just a way to expose the files that we are editing here in the source folder. Okay, great. So I'm going to create a new terminal. Let's just run yarn. This is to install every single dependency that we have on the package JSON. It will install ethers and also the webpack dependencies that we need for the example. Let's just wait a few minutes. And okay, it's building some packages. And well, while we are waiting, you can open your Ganache if you want. I'm using Ganache just to keep it simple. But you, as always, you can upload it to Infura or whatever you want. So, okay, this is done, and let me just open Ganache. Okay, there it is. Okay, create just a new session with quick start. And I'm going to continue with the example just to let it load. Okay, great. So now that we have every single package installed, we can run yarn start, which is going to run this script. And this is going to create our server. So here it is. We can go to our browser and we can check it out at localhost 9000. If you are wondering where this 9000 was set, it was set in this configuration here. So if you want to change it for any reason, you can change it here and rerun the script, and it will show up in the port that you selected. Okay, great. It is actually running, and it has the hot reload enabled. So whenever we change anything here, you might see that this is going to reload. But just let's see what we have in here. We have two interfaces. Let's suppose that everything is in the same page. Let me just open our DevTools. And let's do some zoom here. Okay, great. So we have first the Ether Vault. You have a title with your balance, which is going to be fetching the amount of Ether that you have in the Ether Vault. And also you have the Ether Vault contract balance, which is the total amount of money that you have on the contract. Great. I'm seeing the joke that Benson has told us. Great. Okay, cool. So now that we have this one, we can start filling out the functions that we have here. So let's see which are these functions. So we are using these elements, these UI elements here, which is the deposit, and this is corresponding to this amount and this button here. So we can use this form to hear the onSubmit event. So we can send on the onSubmit event a call to the contract and then do the deposit. And also the same with the withdraw. The withdraw has this form, which is this one, and also the amount, which is the input. Okay, great. So we will start with these calculate vault balances, which is the one that is also called whenever we click on this refresh button. At this moment, we have anything here, so it is not working, but we are going to fix it. Okay, so the first thing that we have to do is to deploy some contracts in order to interact with that. So we are going to create these contracts here. Let's start with the Ether Vault. That's all. And we are going to start coding the example that we have. Let's start with pragma solidity 0.0.0 contract Ether Vault. And we will have a mapping, which is going to map address to uint 256, which is going to be public, and this is going to be the balance. Remember, the public visibility here will create for us the getters for the function, so we can just check the balance whenever we want. I'm missing a T here. Okay. Next, we're going to set up, well, we won't need a constructor. We're just going to need two functions, the withdraw function and also a function which is going to be external and payable according to Solidity documentation. And this is going to be our fallback function. Great. We are missing the public here and also the payable. Great. Next, we are going to receive one parameter, which is the uint 256 amount to withdraw. And then we are going to use a require to validate that nobody, nobody is going to claim more Ether than he actually has. So, okay. We are going to check that our balance in the position of the message that sender should be great or equal at least than the amount that we want to withdraw. Great. Then we are going to create our security flow using message.sender.call.value, and we are going to send the amount to withdraw, and then just calling that function. This is the part that we are going to use to send, as said before. Note that there are some warnings here because, yeah, this is something that you are not supposed to do, but we will assume that this is something that is okay. Okay, cool. Now we are going to register the amount that we withdraw using this to withdraw. Great. And finally, using our fallback function, we are going to use register the amount that we sent. Use plus equal message that value. And there is, let's just run Truffle compile to see that everything is working correctly. And disclaimer, you have to have Truffle installed globally. If you haven't already, do it with npm install -g, and you will have the Truffle installed globally. Okay, there is a completion error here. This is because I'm using another Solidity compiler version. Let's just move into the Truffle config. I'm going to uncomment this line, and I'm going to specify that I'm going to use the the fifth version. Okay, great. Let's just Truffle compile again. Let's wait, compiling. And again, we have a problem here. Okay, great. This is because since version 5, we have to specify some bytes input here. It doesn't matter that it's only an empty string. It is enough to fulfill the requirement. Let's just try it again. Okay. It's taking actually a while. So I'm going to try for the next contract to just code it and try to do my best to so I don't have to compile it many times. Okay. There is just a warning, which is this one, which is okay, and everything just compiled correctly. So we have here our build functions. There is the ethervault and there is the migration artifact. So it is okay. Great. Now we have to create our hacker.sol, which is going to be the important part. Let's start with Pragma Solidity in the same version, 0.5.0, contract hacker. And this contract will have two variables and our constructor. So we will start with the variables. We'll start with the variable of type ethervault, which is going to be public, just to check what is the address of the victim. And we will call it victim. Note that there is an error because there is no identifier for this type, and this is because we need the source code of the original contract. So this is why you need the source code, and you have to find it whenever you want to do something like this. I hope you are not going to do it, but yeah, let's just import it from our ethervault.sol file, and that will fix it. Okay, great. There is no error. Again, only here a problem with the compiler, but this is something regarding my versions on my VS Code, so don't worry about it. Okay, so now in our constructor, we are going to save constructor, and it will receive an address. This address will be the address of the victim. And on the victim variable, we are going to save an instance of the ethervault at the address that we are going to hack. Great. That's everything for that. Let's just add an integer here, which is going to be public, and it will be our count. We will use this at the end of the exercise just to see how many times did we perform the attack just before we run out of gas. So it will be for that. Don't pay too much attention to that, just to show you. You can avoid it if you want. And again, we're going to code some functions here. The first function will be the attack function. And this function will be calling the victim that withdraw. And let's say that we are going to withdraw one ether, just for simplicity, but you can actually receive an integer here and, pass it as a parameter to this withdraw function, but we are going to keep it like that. Great. Our next function will be the function for deposit. This deposit is going to be the way in which the hacker contract is going to send its funds to the Ether vault. This way, the hacker contract will have a balance on the Ether vault. So we are going to just call the address of the victim. We are going to use this constructor in order to get the properties of an address, because at this moment, victim is just only a variable which is representing the instance of the contract. So if we call the address, we are going to get every single capability of the address. So now that we have this, we are going to use call and then use value to send, let's say, one ether again, and just calling that function with an empty byte 32 here. Great. We need also our function fund. This is a completely empty function, which is just going to be public and payable. Actually, I need the public here and the public here. Okay. Let's code the withdraw function. And this withdraw function, as you know, is going to be the way that we are going to get every single letter with stole out of the contract. So it is a public function. It will be using the same method to transfer with the message that sender that call that value. And here we need to know how many ether the contract has. And the way for doing that is just using the address constructor again with the this value, which is the contract that we are using right now. And just set value, no, balance, sorry. And then again, just calling this function, right? And finally, where the magic happens, we are going to create our function, which is going to be our fallback, which is external payable. And here we're going to count just to check at the end how many times we did the hack and perform an attack here. And that's great. I think everything is complete. So great. Let's try to compile it to see if everything is working correctly. Actually, I think I'm missing a payable here. I'm not pretty sure because this is, as far as I remember, this is, since this is using, this is sending ether to the other contract, this problem needed, but I don't know. I'm just gonna leave it like that in order to avoid some problems on the future. Okay. Also, I needed the public in this constructor. Great. Let's compile it again. And just wait, because it is taking a while every single time I compile. Okay, great, everything's passing. Okay, so now that we have our contracts done, we can move to our migrations. Let's just copy the content of this initial migration and create another migration, one for deploying the ether vault. The thing here is that we, instead of requiring the artifact of migrations, we're going to require the ether vault artifact. And finally, we are going to use another migration to deploy our hacker contract. And actually, we have a problem here. We can replace the same, but we have a problem here. And the problem is that the hacker contract receives one parameter here, which is the address of the victim. But at the moment, we don't have that address. Well, actually, we have, but we have to access it in some way. Great. Okay, cool. So in order to have this address, we are going to require also the ether vault artifact. This is because whenever you deploy something, Truffle automatically registers the address on a section that is called networks here. So whenever you deploy anything, you will see here the ID of the network. Let's say for mainnet we have 1, and then we will have here the address with some other information, right? So we can actually use in the middle of the migrations this network address in order to, deploy our new hacker contract. So I'm gonna leave it just like it was at the very beginning, right? And let's move it to here. Okay, so since we are going to use Ganache, which is already working here, we're going to use the network ID 5777, which is the standard network ID for Ganache. So here as a second parameter, we're going to pass the ether vault that networks in the position of the network ID 5777 that address, and this will do the work for us. Great. Seems like everything is fine. Let's just try to migrate this. And we have to wait. Okay. William, thank you. Thank you for the accomplish. Yeah. And also Tyler, you can also access the address on the deploy instance. Yeah, actually, we can use this here. We can actually use something like, let me just copy this line. We can use something like await that deployed and then that address if I don't miss it. Something like this. Yeah, thank you for the, yeah, great, Tyler. Yeah, these two are actually the same. So whatever you want to use, it's okay. And this actually, I think this one is better because this one is going to take the network ID of the network that you are using when you are deploying. So for example, if you try to deploy this one, for example, in Rinkeby or mainnet, it will always use this one. So I will try to use this just in case. Great, thank you, Tyler. Okay, cool. So let's see what happened here. Oh, okay, great. We don't have any config for network. So just uncomment these lines here, which is communicating to our Ganache, which is in localhost in the port 8545, which is this one. Okay, everything's great. Let me try it again. Let's just wait and see if this worked. Just wait. Remember always that we are, every time we're migrating, it will again compile our contracts. So I think that's why it take a while the first time. Okay. Tyler, but your migration function is not async yet, so it might not work right now. Oh, yeah. And that's actually what happened here. Thank you. Okay, let's move this to an async function. And let's see. Actually, it seems like, yeah, I think it was the problem. Let me try it again. Okay, just wait a few seconds. Okay, and there it is. Okay, look that this time it only deployed our hacker contract because the other ones has been already deployed. So this is something great about migrations. If you want to do the whole process again, you can just do it with reset, and that will be that will do everything again. Okay, great. So let's see on Ganache, we have here two contract creations, which is weird because we are supposed to have three. I don't know what happened here. Let me just do a reset because I'm not pretty sure if this was deployed actually. Okay, and now that we are waiting, let's move on onto the source folder. And here in our source folder, we are going to start with the calculate vault balances, which is going to be this function right here. Okay, great. Let's see how is the migration going. Seems great. Number 2, number 3, and that's great. Okay, cool. So now that we are set with the smart contracts, we can continue with these calculate vault balances. And for that, we are going to use ethers to check first the amount of balance that we have on the contract and also the amount of balance that the contract has itself in Ether. So for that, let's just first calculate the vault balance. And for that, we are going to be using an await. And we are going to use the provider that we get when we connected this application to MetaMask, which is this one. And this is using the provider of the browser. So we just have to do a wait provider that get balance. And since we already have the instance, actually we don't have the instance, but that's a problem. We need the instance of the contract. Let's just leave this like that and go to this part of contracts to create the instance of the contracts. We need two, the first one for the Ether vault and the second one for the hacker. So let's start with the hacker vault. And we are going to create a new ethers contract. And this will receive three parameters. First one, the address of the contract, the ABI, and finally our provider. And at the end, we'll have to connect this to our signer, which is this one. This is because ethers give us capabilities to connect to a smart contract, but only in a read-only way. So we need to, at the end, do a connect with the signer, and this will allow to do state mutation operations with the smart contract. So great, let's just replace this address. And for that, we're going to import the artifact, the JSON artifact, which is here. So let's just do ether vault artifact, and we will require it from build contracts ether vault. There it is, and let me just duplicate this line to have the ABI and the artifact of the hack contract. Okay, great. So This is Ethervault. Great. So we will start with the first one, which is going to be the Ethervault that networks. And we will assume for this example that we're only going to use the Ganache. But again, you can always check the network that MetaMask is providing you to the browser in order to put it here. But since we only deployed our example on Ganache, we're going to use the 5777 again. So that should be enough with the others. Great. Now for the ABI, we have to just call the ABI, and the provider is already set. Great. Let's just copy this line, but instead of the Ethervault, we're going to set up our hacker instance. And great. Cool. So now that we have these instances, now we can calculate this balance. So we can just get the balance of the Ethervault. Let me just be sure of that. Yeah. Ethervault.address. And we can, since we have here the Ethervault contract balance, and there is a tag to hold the balance, we actually can use this element to insert the number into the user interface. So this element is here, Ethervault balance and my balance. These two are one for the balance of the contract itself, and the other one is for our balance in the contract. So let's use the Ethervault elements that balance, and we are going to set the inner text to ethers.utils.format units, because this is needed because the balance that the provider give us is going to be hexadecimal. So we have to parse it here. Old balance with 18 decimals. And great, I think this is currently working. It cannot read property address of undefined on here. This is the problem, the hacker artifact. Let's see what's happening here. We have networks, and we don't have anything here. I don't know why, which is the same problem that I was having before, because this is not going. Let me replace this with the address. And I'm going to destructure this in order to have. Great. Let's see if this works. If not, I'm going to use my original implementation. So I'm sorry, Tyler. Actually, I thought it was a great option. But yeah, let's see if it works. Just give some seconds. Okay, first one, second one, okay. And again, I'm having some problems with this one. I'm going to use the original one just to see if there is any problem with this async property of the function. Okay, so I'm going to use the hacker that networks in the 5777 address. Okay, and I'm thinking probably this is because I'm requiring the artifact. I don't know if this environment is the same as the Truffle console. So since I'm not pretty sure about it, that's probably what's happening there. But I'm not pretty sure actually. Okay, again, it is starting. First one is okay, second one is okay, and the third one, oh, this is the problem. Okay, let's just give it another try. It needs to be Ethervault address, right? Yes, it needs to be it. I mean, we can hard code it since we have already here on the transactions, but I'm gonna try to do it the right way. So let's just wait for the next migration. Okay, there it is. Great. So it worked. Cool. So we can continue. Let's see just in the browser. And there it is. Here we have our balance. The balance of the contract is 0 because we have no ether there. So let's continue with the code. Um, Great. So the second thing we need is to calculate the amount of balance that we have on the Ether vault. So let's just get our address using await signer.get address. This is going to return the address that is connected through MetaMask to the browser. And also, let's calculate the balance using await Ether vault that balance. And we are going to calculate that balance using the address that we got. Let me copy this line because we are going to use the element of my balance to save this balance. Great. There is a 0 here and a 0 here. Let's just complete these two functions here, which is the deposit and the withdraw. Is this one and this one. Great. So we will start by completing this. Actually, this is not. This is the one that I was searching for. Okay, great. So since this is called by a submit event on the form, we are going to we will need to prevent the default behavior of the form, because if not, the page is going to reload every single time. So we have just to do a event that prevent default, and this will avoid it. Because at this moment, if I write whatever here and I click deposit, this will reload the page, which is not what I want. Okay, so now I'm going to save this. Great. And the second thing that I'm going to use is going to be transaction, send transaction. And this transaction is going to be sent to the address of the Ethervault. Ethervault that address. And it will be with the value that is in the input. The input is going to be this one. It has an ID with bold deposit amount, and this bold deposit amount is here. So we can access it like that, and we have to parse it using ethers. So we are going to use ethers.utils that parse ether. And here we're going to use the Ethervault elements that deposit that amount. And this is going to return the input. So we are going to access it using the value of the input. And there it is. So now we just have to come back here. We can start by sending. Let me import my 12 words here, so I can use the accounts that are in Ganache. Okay, great. Restore. And there it is. Let's just move to here. And I'm going to deposit, let's say, 10 ether. And oops, I think the prevent default is not working, and this is because I put everything here and I was trying to complete this function. I'm sorry. Okay, there it is. I'm going to try with 10 ether. It needs connection with MetaMask, so I'm going to approve every single account so I don't have any problem in the future. Okay, I'm clicking on deposit, and again, it is not working as expected. The prevent default is okay. Let me try it again, and there it is. Okay, so I will send 10 ether to the ether vault. Let's just wait and we can be refreshing this. Let's just see what happens here in Ganache. Let me reload the page, and there it is. I don't know what happened with this refresh button. Probably it is not enabled. We're going to find out later. Okay, great. So now my balance is 10 and the total balance of the ether vault is 10. Let's say that we have another guy, another fool that is going to send their ethers to the ether vault. So this guy is going to deposit, let's say, 5 ether. And there it is. Let me just ensure that this is on the on click. Yeah, I think everything is okay. So let's see if clicking on refresh. Yeah, there it is. Okay, so my balance for the second account is 5 plus the 10 ether for the other balance for the other guy is in total 50 ether in the ether vault. Now let's enable the hacker contract. We have to first complete the calculate balances. We're going to calculate 2 balances. First, the hack contract balance itself and the hack contract balance that it has in the ether vault. So this way we can check how many ethers does the hacker has in the ether vault. Great. So in order to do this, let's just create a constant, which is going to be the hacker balance using the provider get balance and the address of the contract. Great. And we are going to set this into the balance, the elements, the UI elements we have. The inner text is pretty much the same operation that we already did before. This is going to be either utils that format units. This is going to have the hacker balance and 18. Okay, great. Let's see if this is working. When it reloads, it should be, oh, sorry, I have a typo here. Okay, great. So now we have 0 here. We have to check how many ether does the hacker has in the contract. So in order to do this, we are going to check hacker balance in bold. Into await provider. No, actually this will be a query to the ether vault that balance, and we are going to pass the hacker that address. Great. Let me just copy this, and this element is going to be vault balance. Here it is. This is the hacker balance in vault. There it is. Let's save it. Once it reloads, we have our zeros here. Great. So at the end, we just have to complete this. This refresh is actually working because it is already connected to this function. This form to fund our hacker is the one that we have to complete. So let's complete it. Okay, we are going to start with the event that prevent default that we did before. And we are going to use our hacker contract with the fund function. This is why we need a fund function. So we're going to send just the value ethers.utils.parse ether, and we are going to use the hacker, the form fund, and the amount, and we are going to check the value. There it is. So let's say that we are going to use user3 for this example. This one, and this is the guy that is going to hack everyone. So he's going to send just 2 ethers to the contract, so we can be, let's just use 2.1, and I will explain why later. But he will send, okay, let's say 3. Okay, so we are going to send 3 ether to the hacker contract in order to fund it. So there it is. We just have to wait until this happens here in our Ganache. If we refresh, let's wait just a few seconds. There it is. We have a hack contract balance in total of 3 ether, and the balance of the hacker contract is 0 because we haven't deposited that into the ether vault. Great. And the reason why I said 3 is because, as you remember, our hacker contract is trying to send 1 ether, and also he needs something else to pay the gas. So if we only send 1 ether, there will be a problem, and the transaction won't be executed. So it is better to have a little more just to ensure that everything is correct. Okay, great. So now we have to complete this function, which is the deposit hacker. And this is pretty simple, actually. This is just calling the deposit like that. Actually, it will be the same for the attack. And this is because those functions don't need any parameter. And actually, we don't have this async because we are just going to call it. We are not waiting until it ends because we are going to use the refresh button. Great. And finally, with the withdraw hacker, we just have to do the same, but with the withdraw. Here it is. Okay, it has already reloaded. Okay, we have a contract balance of 3. Let's deposit 1 ether to the ether vault. So let's confirm. This is the transaction, I think. And let's just refresh. There is 2 in the contract balance of the hacker contract, and 1 of the hacker balance in the ether vault. Let's just do it again because once when I was testing this out, I had several problems with the amount, so I just want to be sure that there is enough. So I'm going to do it again just to be sure about it. Here is again our new transaction. Let's just wait until the refresh works. And there is, we have 2 ether on the ether vault. So now we just have to call the attack function. And just before I click on the button, let's just verify how many ethers do we have in each account. For example, the account 1 has 89.9 because of the 10 ether that he sent to the ether vault minus fees. And in the account 2, he has 94.99 because of the fees and the 5 ethers. So the total balance of the contract, of the ether contract, should be at this moment this 15 plus the 3 that the account 3 has already sent it. Let me just refresh it, and as you see, there are 17 because there are 2 here. Great. So now let's just do the attack. Let's just click in here. It will call the function attack. It's a normal transaction. It has not pretty much information here, just the call to the function. Then we can confirm, and we have to wait because here it is. We can refresh, and there it is. Actually, we get the 2 ether back plus a little extra. That's why we have 4 here. And yeah, there it is. And this here is another vulnerability that it has. That is a consequence of the reentrancy attack. This is called an integer underflow because this ethervault was extracting from the balance of the guy that was trying to withdraw the amount he withdraw. And since he withdraw more than he actually had, this caused a reset on the counter. So this is also another problem, that we are supposed to have an infinite balance on the ether vault, on the original ether vault. So this hack with this configuration give us only to install 1 ether, which is actually pretty great if this were in mainnet. But I think we can actually do it again. Let me just try it and let's see what happens. Confirm. Let's just wait. There it is. We can refresh this. And seems like nothing happened. I'm not pretty sure why. Probably because something inside this contract. But yeah, I think at this moment what we can do actually is to withdraw the funds and take the bounty. Great, we can confirm this. We can check how many ether we have. This is the withdraw, it is pending. And there it is. As you can see, we have 100 ether plus 1 minus fees, obviously. But this is the effect. We can always play and try to change the configuration of the contract. Like, for example, we can go to the hacker contract and change this 1 ether and change it to any value that we want. So we can test how many actual calls we are doing using the vulnerability. Okay, great. So finally, we just have to check how many reentrants do we did using this count. Let me just enter to the Truffle console. Let's wait. Okay, there it is. So I'm going to declare an instance, which is going to be my hacker.deployed. Let me just do this with an await. Okay, so now I have my instance here, which is pretty great. Let me just call with instance that count, and this is supposed to be returning the number of times that we did the attack. And there it is. It seems that we only did the reentrancy 3 times, which I don't know, but this is probably because of the configuration that we have. If you change this for some reason, it will probably get more reentrancies. So actually, I think if we try to withdraw less, probably we can get less, I think. Well, yeah, it's a question that you should play with this in order to see what happens with different values. But yeah, we did it 3 times in a single transaction, which is kind of great, but we can optimize it. Okay, cool. So that's almost it. The only thing that we left to say is that if you want to check the complete solution or the complete setup, you can go to the completed branch on the original repository. And here you can have every single line of code that I actually did in this tutorial. And also one thing that we didn't was this function, the withdraw ether vault. You can complete it, but it is not needed for the hack. We already did it, and we didn't need this function. But yeah, and actually you can test this in Remix or some other environment more friendly for you if you want. But that's basically everything. So great. Let me just go back to the presentation. And great. So cool. I thought I had another slide, but I hadn't. So great. Let me know if you have any question. As I said, the code is here. You can go to the branch, which is the completed branch, and it has every single line of code that we did. Okay, great. So thank you, Scott. Nice demo, Ernesto. Well done. Thank you. And Saul, 10 of 10, best session I've been in yet. Thanks to you guys. So I think you have my contact email and also my Twitter and LinkedIn, so we can stay in touch later. So thank you all, and I think that's it.